Hi, I'm Camillo. We are Team Atlabotics from Ireland.
Hi, I'm Dipshika.
Hi, I'm Ali.
Hi, I'm Abdullah.
And this is our robotic setup. We are using a UR5 robot with an anti-gripper and with custom-made finger for grabbing the pen. And for the visual part, we are using a RealSense D435.
So the system architecture is divided into two main stages, the perception stage and the manipulation stage. The perception stage has an input of the RGBD image obtained from the RealSense camera, which is used to conduct the board localization, the button detection, the shape detection, text command detection, and the maze trajectory projection. Now the output from these stages are either TFs, the button status, the structured commands, all of which are further passed down to the manipulation stage. The manipulation stage is mainly comprised of the MoveIt task constructor, which is used to generate the path and the poses in either the Cartesian or the interpolation space. Now the output from these stages are directly passed to the ROS2 UR driver, which further moves the robot and controls its motion. For our board localization task, we have focused on reusing the code from a previous team, Team Robothon. We have focused on optimizing the code to make it compatible with ROS2, use the inference using YOLO V8, and most importantly, use it for publishing the TF of different components that are detected on the task board.
For the button detection task, we use OpenCV based image processing to detect which button is glowing for the robot to press it. For that, we have created HSV ranges for both glowing and idle buttons, both red and blue, to detect changes in their light intensity. The logic for this method is that if the detected HSV is in the range of red glow and blue idle, we simply publish a message saying red glow. Similarly, for red idle and blue glow, we publish a message saying blue glow. Based on these published ROS messages, the robot presses the button which are already detected in the localization from task 1. For the shape detection tasks, we again use OpenCV based image manipulation techniques to extract and approximate the shape displayed on the touchscreen. The robot reaches a predefined position atop the touchscreen which was detected during the localization in task 1. A white mask is created along the edges of the touchscreen to restrict the detection inside the screen region only. The distortion caused by the progress bar circles on the top of the screen is removed using specific radius range in half circles. The main shape, which is shown in red on the screen, is then isolated and skeletonized using red color mask. At this point, the image may be distorted, so we use fit ellipse or approx poly-TP to approximate the skeletonized contour and determine whether the shape is a circle, triangle, or square. The ordered pixel endpoints of the detected shape are published to the ROS topic detection point for tracing of the robot.
For the text command detection, we depended on a VLM model, Mondream 2 billion, to extract the text of the task from the screen, and then we pass it to an LLM model to create a structured task in the following format to handle the random nature of the task generation. If the action ID was 0, it indicates that it's a simple movement from 2 points. If it is positive, it means that it is repeated action, and if it is -1, it means it's a long action. This structured task will be published.
To address the main task, we have decided to record one execution of the path with respect to the board, and then reproject this on the new position of the board when we will move it inside of our workspace. To control the motion of our robot, we have decided to use MoveIt task constructor. And our idea is to associate a set of MoveIt tasks to each movement of the robot. For example, pressing the red button or picking the stylus. Then, MoveIt task constructor allow us to have a high control on the creation of each sub-trajectories during each task.
So based on the MoveIt task constructor, we are using a configuration file in the structure shown here that will allow us to send any kind of move goals to the MoveIt task constructor. Now this allows us to play around with any task in any particular order and provide it in different stages of operation. So for example here, if an input is given in the form of a text like move to a location and pick the stylus and press the button, the robot will be able to execute it since the VLM will translate this text into a configuration file which can then be loaded by the robot and further executed. So Based on this configuration file, we propose our bring your own device idea that can help us translate any task that can be an input through a visual source, through a textual source, which can then be converted to a configuration YAML and then further translated to the robot.